In this video, we're going to talk about a couple of common special series. The first one is the geometric series. So geometric series, you're just multiplying each term by a common factor, and this is what the general form looks like. So we're going from n equals 0 to infinity, typically. A is a constant. It's also the initial term because when we plug in 0 for n, we get r to the 0, so basically that goes away. So A is the first term of a geometric series, but A and r are both just constants. So when the absolute value of r is less than 1, our geometric series is going to converge. When the absolute value of r is greater than or equal to 1, it diverges, and then the sum of a geometric series is a, or the first term, over 1 minus r, and r is that factor that you're multiplying each term by, which will make more sense in the example on the next page. But make sure this is all stuff that you need to memorize. Alright, so here's an example of a geometric series. Does this series, the sum from n equals 0 to infinity of 300 times 0.45 to the n, converge? And if it does converge, what is the sum? So the first thing I do, looking at my series, I see that 300 is sort of in front, so that's going to be my a, and then my r is the thing that's raised to the power, because that's my common factor. That's what I multiply by each time, for each term. So I notice that this is a geometric series, and when I'm writing out my answers, I have to justify everything, so that's why this entire thing is written out. So my series is a geometric series. The absolute value of r is the thing being raised to the power, so 0.45, and that is less than 1, so because it's less than 1, my series converges. So I need to say all of these things. I have to say it's geometric, I have to say r is 0.45, I have to say 0.45 is less than 1, and I have to say that it converges. That needs to be in my explanation, especially if this is free response. And then the next part, it does converge, so I can find the sum, because that's what it means. If it converges, it has a sum. So the sum is a, which is my initial term, or the thing that's not raised to a power, 300, over 1, and this is always a 1, minus r, which was 0.45, and then if I figure that out, I get 545.455. A geometric series, we didn't talk about the definition before, but a geometric series is one where you multiply by the same thing for each term. So if you look at this sequence, this series up here, 5/3, 5/6, 5/12, and 5/24, you'll notice on the bottom we're multiplying by 2, and on the top we're multiplying by 1 each time, because 3 times 2 is 6, times 2 is 12, times 2 is 24. So this is my key that it's a geometric series, and a geometric series always has this form. So basically I just need to figure out what is a and what is r. A is always going to be our initial term, which means like when n is equal to 0. So I just look at the first thing in my series and I see 5/3. So my 5/3 is a. And then to figure out r, I have to figure out what am I multiplying by each time. So this one, I kind of split it up because it's a fraction. So I looked at the bottom and I saw that I'm multiplying by 2 each time. So I put a 2 on the bottom of my fraction. And then I noticed at the top I'm multiplying by 1 each time. So I put a 1 here, which means that my r is equal to 1/2. So that's how I can turn this series into a more generalized formula, put it in sigma notation. Alright, so here are some for you to try. These are all geometric series, and all you have to do is determine whether it converges or diverges, which means we're looking to see how r compares to 1. And if a series converges, you need to find its sum using that formula that we had on the very first slide about geometric series, the a over 1 minus r formula. Some of the series for like number 2, 3, and 4, you're going to have to rewrite these to make it look more like a geometric series, because we always want to have it in that a times r to the n form. So do that first before you figure out whether it converges or diverges, because that'll make it a lot easier for you. Alright, so pause the video here and try these, and then when you're ready, go ahead and turn the video back on and we'll talk about the solutions. So for number 1, that's a geometric series. The absolute value of r is, well, r is pi over 3, which I know is pi over 3, which is greater than 1 because pi is greater than 3, so this has to be bigger than 1, which means that our series diverges and we can't find the sum, because diverges means that it does not have a sum. Alright, the second one doesn't look maybe like a geometric series to start with, so I have to rewrite it as a geometric series. So I have 1/2 raised to the n, because technically we can think of 1 as being raised to the n power, so then I can factor out that exponent. So it's a geometric series. R is 1/2 right here, and the absolute value of 1/2 is less than 1, so that means that our series converges, which means we can find the sum because it's geometric and it converges. We need both of these to be true for us to find the sum. So we have A, which in this case is just a 1 since there's not anything here. So we have 1 over 1 minus 1/2, which simplifies to 2. And this is actually the same series that we found in the last video. We found that the sum was 2 using partial sums. Alright, number 3, we have 1/2 plus 1/6 plus 1/18, etc. And this one's a little bit harder, so we need to start by writing it as a geometric series. Notice that each of them, like, you can rewrite, well, 2 is just 2, but 6 is 2 times 3, and then 18 is 2 times 9, or 2 times 3 squared. So really we have 2 times 3 to a power, and then we can split that up by bringing the 2 out front, so we have 1/2, and then we have 1 over 3 to the n, which we saw from the last example. We can factor out this n here. So 1/2 is my A, and 1/3 is my R. So this is now well, even before this was geometric series. So it's geometric. R is equal to 1/3. 1/3 is less than 1. So that means that our series converges, and then the sum is A, which is 1/2 over 1 minus R. Simplifying that, we get 3/4. And for the last one, this one looks more geometric. We have 3 to the n over 2 to the n. So because they're both raised to the n power, I can like undistribute that n, and I get 3/2 is my r raised to the n power. So this is geometric with r equals 3/2. 3/2 is greater than or equal to 1, so that means our series diverges and there's no sum for it. The next series, this is just one that shows up commonly. It's called the Harmonic Series, and it's the sum from n equals 1 to n equals infinity of 1 over n. So that looks like 1 plus 1/2 plus 1/3 plus 1/4, and so on and so on. All you need to know right now is that this series diverges. We're going to prove that later on, but right now we don't have a super easy way to do it. We could do it with partial sums, but coming up in later videos, there's a much easier way to show that this doesn't converge. So you need to know the name, the series, and that it just diverges anytime you see it. Alright, and here's the reason that we talked about a harmonic series, because now we have the P series, which is sometimes called a hyperharmonic. And a hyperharmonic wouldn't make any sense if we hadn't seen what a harmonic series looked like. So the harmonic is just 1 over n. P series is 1 over n, where n is raised to the p. So for a harmonic series, p would just be equal to 1. But for the P series, this is a more general form of it. Alright, so the P series converges when P is greater than 1, and it diverges when P is less than or equal to 1, which seems kind of backwards from the geometric series, but this is also something that you need to memorize because the P series shows up a lot. Alright, and here's an example of what you might see with a P series. We're trying to figure out, does the series, the infinite series of 1 over the cube root of n converge or diverge, and we have to justify our answer. Even if it doesn't say justify your answer for a question like this, you need to justify your answer. It's just assumed that you should include an explanation. It's not reasonable to just write converges or diverges for the answer. You have to say why. Alright, so we have this series. It doesn't maybe look like a P series, but we can rewrite the root as a power. So now we have 1 over n to the 1/3, and that is a P series because I have n raised to a power. So P series, P is equal to 1/3, and 1/3 is less than 1, which means that our series diverges. And that's all we have to say about that. We don't have to worry about a sum or anything, especially because it's diverging. Alright, so here are some P-series problems for you to try. Determine if they're convergent or divergent. You don't have to find the sum because this is much harder to find the sum of than geometric series are. Make sure you justify your answers, so you need to have an explanation with each one of these. And pause the video, and then we'll talk about the solutions for this. Alright, for our first series, we need to rewrite that as a in sigma notation, as a summation. So we end up with 1 over n cubed, because this is 1 over 1 cubed, 8 is 2 cubed, 27 is 3 cubed, 4 cubed, and 5 cubed. So this is a p-series. My power is 3, since everything was cubed. 3 is greater than 1, which means that my p-series converges. And that's it. The next one, we have n to the negative 2, which maybe first glance doesn't look like a p-series, but we can rewrite it as 1 over n squared. And now it's definitely a p-series. So my p-series has p equal to 2, because that's the power. 2 is greater than 1, so that means it converges. For number 3, this is like the opposite of what we did with the geometric series examples almost. There's a power out here, but we can distribute it to each one of these. 1 raised to anything is just 1, so that'll just be 1. And then on the bottom, we'll have n to the square root of 2. So this is a p-series, square root of 2, and I know that square root of 2 is bigger than 1, so that means my series converges. And then for the last one, this definitely doesn't look like a p-series, but we could write it as a fraction. So right now this is n to the first power, even though it doesn't have a 1 written there. It's just assumed. So what we could do, instead of having n to the first, we can move that n to the first to the bottom of a fraction, but because we changed what side it was on, it needs to be a negative exponent now. So we have 1 over n to the negative 1, and those two are equivalent to each other. So this is a p-series. P is equal to negative 1, which is less than or equal to 1, because this time we're not doing absolute value, we are just looking straight up at p. So p is negative 1, which is less than 1, so that means that this series diverges. And you'll notice we also showed in the last video that this diverges because this is just 1 plus 2 plus 3 plus 4. And it diverges based on its partial sums as well, which is good because they should match. Alright, and that is it for now. In the following videos, we will learn even more ways to figure out if series converge or diverge.